Welcome to Chapter 10 of the C++ programming language by Bjarne Stroustrup. Chapter 10 looks at expressions. So my current plan is to split Chapter 10 into two videos because the first half talks about writing a very specific program, and the second half looks more at back to normal stuff with syntax and different keywords and stuff. So they do feel kind of separate. It's all Chapter 10 though because they all are relevant to expressions. But we'll see. I'll decide that later. So I'm not bothering with the introduction because I think 10.2 really gets to the heart of everything quite quickly. So 10.2 looks at creating a desk calculator program or a calculator program. Creating a calculator program. So the premise is we want to create. Already writing small. We want to create a desk calculator program, right? So as you would with your, something that's capable of adding numbers, multiplying, dividing, and subtracting. So we have plus, times, right? Asterisk is times, division, the slash, and subtraction, right? The minus sign. So the four operators should be available, and we should also be able to define variables. Okay? And then the question is, well, what is the point? How does this program relate to expressions in C++? Well, let's give some input. So if we were to type in, let's say in our program, we were to type into standard input r equals 2.5, right? And then hit the enter key. And then area equals, we'll say pi, asterisk, so times r, asterisk r. So a note here is that let the value of pi, so 3.14, be 3.14, be predefined. So we built the value into the program already. So if the blue is our input, what should happen for our output is we should see that the number 2.5 gets printed, right? Number 2.5, as in the evaluation of r equals 2.5 is 2.5. And then area, when we calculate this, should be, the output should be 19.635. So when we do 3.14 times our 2.5 times our 2.5, our r value, this is the number that should get printed. And the side effect is the value of 19.635 should be saved in area. So if we refer to area later on, it should remember that that's the value associated with area. Now, so like I said, why is this relevant to expressions? Well, you can think of the blue, the input we're providing, as kind of like a mini programming language. Maybe programming language is a bit much, but a kind of language that we're writing in, right? We're giving certain characters, and there's an expectation that the computer is able to understand that language and then give us the output we want. That should say 2.5. I don't know how legible that is. 2.5, 2.5. So in that sense, it's well, what is the kind of way we can take in what are essentially characters, right? R and even the 2.5, they're all going to be characters we're giving to the computer. And the equal sign and the symbols, they're all kind of characters. How can a computer take in those characters and figure out a way to interpret those characters to give us the output we want? So how do we, and that's how we get to this idea of trying to evaluate expressions, trying to evaluate values from expressions. So that's what this is all about. So, so the calculator will consist of 4 parts, right? Like our program is going to consist of 4 parts. So we're going to have 4 parts, primarily the parser, the input function, the symbol table, and the driver. So the most important, I reckon, would be this one. The parser is where we get to the meat of how we are able to read in characters and evaluate a value. So read an expression and evaluate a value. So that's what the parser is going to be doing. Input function, just how we provide input, typing in into standard input. Symbol table is basically how we're going to be able to remember variable names or variable values like R or area. We're going to remember what those values are using a symbol table. And drive is basically, in our case, is going to be the main function, which kind of lets us sort of start the program. But yeah, the main thing we're going to be looking at is the parser and a little bit at the symbol table. Okay. So literally this entire section, 10.2, is writing up the program. That's what we're looking at. So the first thing to do is to kind of give a kind of description of what any kind of input is going to look like. So a general view of the input. So we know, for example, that when the program runs, we have the overall program. And the question is, well, what could the program look like? Well, the program will look like a bunch of expressions, right? Like R equals something, and area equals, and 2 plus 3 times 5, and 6 times 12, and Y equals R minus 3. All of those are expressions. So the collection of them, we call them an expression list. And then after that expression list, we're going to have an end, right? End just means, the end of the program. So somehow, maybe you do Control C or Control V to indicate that you've completed all your input and you want to quit out of it. So that's what the end is for. So expression list is literally just the list of expressions. And what we're doing right now is we're going to try and define our overall program in a kind of recursive way. I'll show you and I'll explain what that means. So in the sense that expression list, we're going to in turn define as well. So if the program is a bunch of expressions, an expression list, followed by the end, right, some kind of end, then an expression list is an expression followed by a print. A print doesn't mean print means something specific, and then another expression list. So let's just break this down. A print, by the way, just indicates the end of an expression. I don't know why the book calls it a print, but you can think of it kind of like as a semicolon or a new line. Semicolon in C++, so it indicates the end of a line in C++, or a new line if you hit enter in your calculator. Print is just that. It doesn't actually mean you're printing. Oh, I guess it kind of does because you will print out output. That's probably why they called it print. Okay, that makes sense. Print is basically when you expect one expression to be evaluated because you're going to print out the output and then you'll have the rest of your expression. So what is it saying? Well, an expression list, the list of expressions, can be thought of, if this is my expression list, it can be thought of as one expression followed by an expression list that is one expression shorter, right? An expression list is one expression plus the rest of the expressions. That's all this is saying, right? So that's what I mean by it's a recursive definition. We're defining it as sort of using itself in the definition, but in a way that's kind of clever or recursive. So, and bear in mind that an expression list can be empty as well. So a program could just be the end by itself without any expressions, because an expression list can be empty. Okay, so that's the expression list definition. But if we define expression list and we have this expression term, we have to also define what an expression is, right? So an expression, this is where my understanding of the definitions kind of took a bit of a turn, took a bit longer to understand. But the way that I'm going to write it in two ways. I'm going to give it the way the book gives it, and then I'll try and break it down. So an expression is either an expression plus a term, an expression minus a term, or a term itself. Okay? Now, we haven't really introduced the word term yet, so we have to kind of just work with it at face value. But in essence, if we have this construct of a term, either an expression is that term, or an expression can be a term plus a sort of shorter expression, or it can be minus a term plus a shorter expression. So kind of in the same idea. If an expression consists of a long chain of mathematical operations and terms, we can think of it as if it's term plus term plus term plus term, right? If this entire thing is considered an expression, it can also be seen that this expression can be written as this slightly shorter expression plus this extra term, which is what this first thing is saying. It's a slightly shorter expression plus the term. Similar idea with the minus, right? An expression minus a term, because an expression can be expressed as a shorter expression minus a term, and we also say that an expression could just be one term by itself without any pluses or minuses. We could say that a term, just by itself, is in itself is an expression. So that's the way the book writes it. The way I would write it is an expression is like a term plus or minus another term plus or minus another term plus or minus another term. So you basically have a bunch of terms with plus or minuses in the middle, in between them. But you have to bear in mind that you could also just have one term by itself. So maybe I'll put it in brackets, like maybe this is here as well. Right, so term, and then an expression is just a bunch of terms added or subtracted from each other. Okay? So that's an expression. But then, like I said, we've introduced the term, the word, we've introduced the construct of a term, but now we have to define what a term is. So what is a term? And it has a very similar definition to expressions, but we now introduced the word primary. So a term can either be a term divided by a primary, a term can be a term times a primary, so asterisk or times, or a term can be a primary itself. So, very similar to the expression definition, except instead of plus minus, we're using division and multiplication. Maybe there's some ideas as to why that's the case. You think of BODMAS or PEDMAS, as to why we kind of have the division and the times are kind of the lower level definition. But in the same sense that this was like a bunch of terms added and subtracted together, a term by itself, that smaller term unit, is actually a bunch of primaries multiplied or divided with other primaries. Multiplied or divided by a primary, and so on. But it could also just be one primary by itself, right? So a term could either be one primary by itself or a bunch of primaries multiplied or divided with each other. That's what a term is. And finally, maybe I should keep this. No, it's fine. Finally, we've introduced this idea of a primary. So what is a primary? And this is where we kind of get to like the absolutely smallest unit of the calculator expression that we can get. So this is where we get things that are more familiar. So we can either have a number, right, like 1, 2, 6.7, like that. Even -3, right, negatives. A name, so the variables that we were talking about, like R and area, those are names, so those will be considered primaries because they should be holding a value as well. Negative primary. How do I do this? No, we'll do the brackets first. Expression in parentheses. So this is really interesting because so far all our recursive definitions have been like involving smaller and smaller units, right? Expression had term had primary, primary had number, name, but now we're bringing back a sort of bigger idea, the expression. An expression in parentheses is considered a primary, and that might seem like a bit counterintuitive because number and name seem like very small units, and then expressions are like whole like longer things. So it's like, well, why is that part of our primary? And when we write up the code for getting this to work, I think it'll make more sense. But in essence, it's to do with this idea that an expression in brackets can be thought of as something that can be evaluated into a single number before it's used for a more outer expression. So we have to evaluate an expression in brackets first, right, because of BODMAS or PEDMAS. And so we consider that part of the primary. It's actually one of the first things that has to be evaluated, even though an expression is sort of more complicated than the typical primary. And the last thing is negative in brackets primary. Maybe it doesn't have to be in brackets actually, but a negative primary. So anything with a negative at the front, and then a primary. So whether it's a negative number, a negative name, a negative expression in brackets, right? Those are also considered primaries. So a negative primary. So this is like the overall layout of what our program will look like. A bunch of expressions, where each expression is a bunch of terms added to each other, where each term is a bunch of primaries multiplied and divided with each other, and each primary is either a number, a name, an expression in brackets, or a negative primary. Okay? I would recommend having that on the side so you can refer to it, especially when you start writing up certain functions. So there's an expression function, a primary function, and a term function that we write up to help evaluate expressions, terms, and primaries. It's nice to have this definition on the side because you see how it kind of carries through and how it's used in those functions. There's something else I want. Oh yeah, notice how. So a primary is a special type of term. All primaries are terms. If you have a primary, then it's a term. Not true for the other way around, right? There is no terms that are primaries, but primaries are a special type of term. So if you want, graphically, we can have a little Venn diagram where primary is a small circle. I'll say prim for short, right? Prim. And then terms are like this. So all primaries are a term, but not all terms are primaries. And then in a similar sense, all the terms are expressions. I'll just say EXPR for expressions. So all the terms in the middle circle are tied to the expressions, but it's not true the other way around. Not all expressions are terms. Okay. I believe, yeah. So that's everything on like how we're going to structure, how everything is structured in our expressions and in our calculator. So okay, so let me put some pens back. If we're going to read an input, of course, naturally, one is probably it's easiest to sort of take it in from standard input, but we say that the parser uses a token stream, right? A stream of tokens. And then what is a token? We'll talk about that in a sec. So essentially, yeah, a token stream encapsulates reading characters. So the function of reading characters is sort of encapsulated or sort of done under the hood by a token stream. So it encapsulates reading characters into tokens. Okay? So a stream of characters is turned into tokens. Now what is a token? A token is a kind value pair. So for example, we could have number and then like 123.45. That indicates what is the type of the token, so number, and then what is the value associated with the token, 1, 2, 3, 4, 5. So we talk a bit more about the kind. So we create an enum class, right? This is where the coding sort of starts. We can create an enum class called kind. And we're going to use some features. All right, this is the other good exercise about this chapter, is like you can kind of see the features we've talked about so far. We're going to make the underlying type char, and the purpose of that will be clear later. But we're going to make the underlying type char, and we're going to give the following enumerators, the following constants. So name is a type of kind, is one of the kinds of tokens we can get. Same with number. Same with end, right? End meaning the end of the entire program, like Control C or whatever. Plus, let me do it in like this. Now I want to start giving some of the enumerators actual symbols to work with. So plus, we're going to give the plus symbol, right? This is kind of why we're making the underlying type chart. Plus, you're going to get the plus symbol. Minus, you can imagine, it's going to get the minus symbol. Same with multiplication. We do MUL is the asterisk. Division, div, is the /. Print, we're going to make the semicolon. Assign, we're going to make an equal sign. Right? So print, assign. LP for left parentheses, we're going to make the opening bracket. And RP, we're going to make the closing bracket. So these are all the types of tokens we should be getting, right? Notice how most of them are actually only one character long, right? So RP, LP, assign, print, all the way up to here. Even end, I can't fully remember how end works, but I'm pretty sure it's like you just control C out of there. But just about all of them are one character, except for name and number. Number will still be characters, right? Obviously, we're trying to get a number out, but when we type things into standard input, it's always characters. We interpret them as characters. So a number might be 123.45. That's six characters because you got 5 numbers in there, 1, 2, 3, 4, 5, and then the decimal as well is another character. So 6 characters there. A name might be however long, right? Area was 4 letters, 4 characters. R was just 1 character. So in that sense, name. It's not super predictable how long a token is in terms of number of characters. Most of the time it's 1, but especially for name and number, it could be any number. So any number of characters. So we can't say, oh, each token is exactly 1 character or anything like that. We can't make that assertion. Now so that's kind. Now I've lost my black pen. There it is. Now we define. I like blue actually. Now we define what a struct is. Now we define what a token is. So we make a struct called token, and we give it 3 things, 3 fields: kind. So that is this kind. We give every token should have a kind associated with it. A string. So this would be in the string library. String val. So if, for example, it's a name, then it should have a string val associated with it, and then a double number val. So if the kind, specifically, if the kind is a number, then the number val should be set to the actual number value. And if the kind was name, the string val should be set to the name of the string, and the number val should be not set to anything. And I believe for all the other types, the kind will be set. So kind might be plus or minus or whatever. But both string val and double val won't have anything associated with them. So that's what a token is. A token is a kind, and depending on the kind, you might also have a string value or a number value. And that's what the enum, that's what the kind, that's what all the kinds are. And the last thing to define, although we don't fully define it yet, but we kind of give an overall idea, is the token stream class. So we haven't looked at classes formally yet, but you can imagine a class as kind of a very special or very cool struct, essentially, with what we call access modifiers. So a class, you have token stream. So you'll see the keyword public, meaning these particular, in this case, functions, member functions, are publicly available outside of the class. So we're going to make a get function, get member function, which essentially, for now, we show the implementation later, but for now, just think of the get member function as given a bunch of characters, it's able to figure out what the next token should be, whether that's 1 character, like a plus, or a bunch of characters, like a number. It's just magically able to figure out what the next token is going to be. And it returns that token, right? Token get. And then the other thing is const token, I'm going to do a reference, current. And what's the point of current? Well, if get gets the next token in your input stream, current gets the token that get just got. That was terrible. Hang on. If there's a bunch of tokens in your input stream, and you call get, right? Get will get this one. And then if you call get again, get will get this one. And if you call get again, get will get this one, right? If you now call current, rather than getting the next token, current will return what get just got. That's what I meant, right? So it returns a reference in this case to the token that was just retrieved, most recently retrieved by get. Okay. So we don't talk about implementation until 10.2.2. So this isn't quite part of the parser just yet. Okay. So, but just bear in mind that we have these kind of magical functions that can return the next token in our input stream, and can also get what we just read in the input stream using the current. Alright, so we will get rid of that. So we imagine that we have the ability to read in whatever token we like because of the get and current functions, right? So now we have to define these three functions. There's the prim function, there's the term function, and there's an expression function. So the prim is able to evaluate any primary, right? So whether that's a number, a name, or an expression in brackets, or a negative primary. A term is able to evaluate whatever term you like. So whatever string of primaries that are multiplied and divided to each other, a term function should be able to evaluate that string of primaries. And an expression can evaluate an expression. So this function down here can evaluate whatever expression. So a bunch of terms added and subtracted to each other, that's an expression, right? The expression function should be able to handle that. Okay, so the book actually defines it in this order of expression, term, and prim. So like top down, like going with the biggest, like figuring out how to do the biggest function, biggest in terms of like handling the biggest input first, and then dealing with the sort of smaller units, term, then primary at the end. I actually think it might be better to look at prim first, like the smaller units first, because they have more detail, and once you get your head around prim, it's easier to kind of pick up term and expression, EXPR. Do I remember how this works? Yes, I think I do. Okay, so let's define prim. So prim should return a double, right? Because we're supposed to be able to get a value out of our expression. Out of our primary, sorry. So double, prim. And we're going to give a parameter get, which is a boolean, so either true or false. Basically saying, should we immediately read the next token before we do anything else? So why do we need that? I think it's more clear when we get to the driver part, but for now, if this is passed and is true, then we will call get. So if get, right, then token stream ts dot get. So the idea is we would have a token stream in the scope, right? We would have the token stream in the scope. I believe in the book, it's like in the global scope, so it's easy to access, but technically that's probably not best practice, but it's fine. For now, think of TS as something in the global scope, and it's of type token stream. So it has the get and current functions available to it because it's public, because those functions are public, right? So what is this doing? It is retrieving the next token, magically, the next token that is in the input stream. And that's if get is set to true. So if get, then we ts.get. Now, we do a switch statement. Switch on ts.current.kind. So we're obtaining the kind of the token that we have just read, whether it's from here, or if this was set to false, then whatever was read previously. But if get was set to false. But we're analyzing and observing the kind of the most current token, right? So we have a few cases. Remember that it's a primary. And so we should recall what the different primaries can look like. So if if the kind of the current token is number, right? That's one of the kinds we have. Notice that I'm using the scope resolution operator because it's an enum class, right? So we have to make sure that the scope is always resolved. All right, so what I'll do is I'll write it like this. If it's of type number, then what we should do is we should get the value double v equals ts dot current dot number value. We also call ts dot get again, and the reason for that is more apparent in a second. And we return v. Okay, so what is this doing? It's taking the ts current, right, the current token, and getting its number value because we know it's of type number. We know that the token is of type number, so we know there'll be a number value associated with it. And then we call ts get. Why we do that makes more sense later. And then we return that value. Now there's one problem with this code, and that is we have done an initialization inside of a case, right, inside of the switch case. Why is that a problem? If you remember back from I assume statements, chapter 9, you can't do that because there's a risk of you jumping over this particular case, but this v would still be in scope, right? So what do we do to make sure this is allowed? If we have to add little squiggly brackets around like this, right, around the case body, because then the scope of v is limited to within this block here. Okay, so that's the only extra thing. So I remember the reason why I point that out because I forgot to write that in, and then when I tried to write up this program myself, it wasn't working, and I was panicking. So make sure you have those squiggly brackets. Now, what if you have type of red? What if you have type name? So case, kind, name, right? In this case, okay, I'll write it out first and then I'll explain it. So, blue. So we're going to make a double reference this time. V equals, I'm going to introduce this table, which is a variable that will be in the global scope. I'll explain that in a second. TS dot current dot string value, right? And then if TS dot get dot kind is equal to kind dot scope resolution assign, then v is equal to expression to true, and then we can return v. Okay. Once again, we are doing like an initialization kind of thing, or some kind of thing, so we want to make sure that we have our squiggly brackets. Right, that's the first thing. Second thing, what the hell does that even mean, right? So, what is a table, right? Because I haven't introduced that yet at all. I kind of forgot to. We talked about the, what was the name it was called? Was it? The symbol table. So the table that basically takes all the names, like R and area, takes all the names, and stores them, and also stores their corresponding values, right? Like 3.14 or whatever. So the way that table is introduced in the book is it's what we call a map. Yeah, I'm pretty sure in C++ it's a map. Sort of like a hash table, whether it's hash table, dictionaries in Python, that kind of thing. Table is considered a map. I forget exactly how to initialize the map. I will put a thing on screen. It will be something like you have to hash include some library, probably like map or something, and then be like I don't want to say wrong stuff, but I'll just say like map, and then you put in the string and the double map or something like this. So what are we saying? I'm not sure exactly what the structure is called, but what the point of the string double is we're going to make a kind of table. Oh, it's called table, sorry, not math. Right? The variable is called table, not math. But we're going to make a table that basically has a string value on this side and a double value on this side. And we're going to put names on this side, like area and pi and r. And we're going to, on this side, put like their corresponding values. 3.14, I think this is 2.5, this is like 19 or something, right? And what that means is, when we write something like this, table, and then in brackets put this thing, right? What this is saying is, get the string value of the current token, right? So whether it's area or, so, because remember, we know that the token is of type name, so we know it's going to be like a name, like a variable name. So like area or r or whatever. Get that string value, get that name, look for it in here, so let's say it's r, and then return the corresponding double value. That's what this is saying. When you have a map that's of type string then double, and you ask for something like this, it's going to look for the string value and then return the double value. So, and that's what this v is going to store then, right? It's going to store the double value, but it's a reference. V is a reference. So it's not going to just store like a copy of the double value. It's actually going to store the double value. It's going to refer to the double value in the map, in this memory. So what does that mean? You know, let's say we're looking at r. V is referring, not pointing, right? It's not a pointer. It's referring to that 2.5. So what is this next line saying? So this top line is basically getting the value of the double. Let's say now that ts.get.kind. So .get means we're getting the next token, not the current token, the next one. If the kind is equal to a sign, why would it equal a sign? Because, for example, we could have a line that looks like r equals 2.5, right? So if the first token was r and was of type name, right, and we did this first line, the next token went from .get, the kind could be an assignment, right? Because it would be that token, then this equal sign. So it could be this. In which case, everything on this side should be an expression, right? Everything on this side should be an expression. So we'd say v equals expression to true. We're going to use the expression function. We haven't defined it yet, but we're going to use the expression function to evaluate what's on this right-hand side. We're going to set get to be true, by the way. Expression will also have this bool get thing. We're going to set expression to be true because we're going to need to read in the next token. And we're going to set v to it, right? So let's say, for example, r equals 2.5 is the thing, which means r hasn't been set to 2.5 yet. V would still kind of refer to this memory. It'd just be that the value of v is empty. It'd still refer to that memory, just wouldn't have anything there. So when we say v equals expression true, the 2.5 will be evaluated using the expression function. We assume that's going to happen. And we say v equals that. That means the memory, right, that v is referring to is going to have that 2.5 associated with it. And that's how we're able to push a value into the double column of our map, of our table, right? So r, which originally had nothing in it, is now going to have 2.5 written in it. Okay? So that's how the name is going to be handled, both in terms of getting a value from a name. So for example, if it's not an assignment, let's say we have area, or we have like r times r, where r has already been set, right? In this case, there's no assignment, so all that's going to happen is v is going to be set to 2.5 by using this line. But if it is an assignment, we have this extra step of actually setting the value of r inside our table. And then we return v. We return the value that v is referring to, sorry. Right? Which is what we want. We want to be able to return the value that v is referring to. Okay, so that's the number and the kind. That's the number case and the name case. Next is the minus case. Right? Get rid of this. What does the number case, the minus case mean? The minus case is for when kind minus. The minus case means that we are about to see, a primary could be of type minus primary. That's the only place where a minus is involved in our definition of primary. So if we see a minus in our token, that means that we basically have to evaluate primary in here and then attach a minus to the end of it. So the way this case is handled is we simply return the minus of the next primary. It's kind of a recursive call. We call prim again within prim. We call prim again, set this to be true because we need to read in the next token, right? Minus our current token is here, so we need to read in whatever the next token is in the primary, right? And we just return the negative of this. This primary refers to this prim true. That's what this guy is evaluating. And then we attach a negative to it because that's what this entire primary is. This primary refers to the primary in here, right, hitting this case. So that's the same thing as putting a negative out the front of evaluating the next primary, which is what this does. So that's what that is. And the last case is case kind LP. That is, we've hit this thing, this definition of a primary, right? An expression within brackets. So what does that mean? Well, we have to then have some kind of evaluation of the internal expression, right? So when we hit this case, the current token is here. So when we ask to evaluate the expression, we set expression to be true so that everything in here will be evaluated, will be read in and evaluated, and we set whatever this value is, we set it to be equal to E. Now, if ts.current.kind is not equal to kind RP, right? What is this saying? By the time expression, the expr function is done, it would have read in this R parentheses, this closing bracket. Why? Because that's the only way it will be able to know to stop evaluating. It's going to be evaluating along here, because for example, I'll write this out properly. And, in brackets, we have basically term, plus or minus a term, plus or minus a term, and so on until the closing bracket. That's what this is going to look like, right? So after this left parenthesis has been read in, we read in this term, and we read in this plus, and we read in this term, we read in this plus, we read in the term, plus, term, plus, term, plus. How does it know to stop? Well, after the final term, instead of reading another plus or minus, it's read in the right parentheses, right? So we know by the time the expression function is done reading, it would have already have read in this right parentheses, which is why we check the current. We check current, not next. We check the current token, and we check if it's not equal to right parentheses. Because if it's not the right parentheses, we know that the user messed up in their brackets. Right? They didn't put enough closing brackets. They didn't put the closing brackets in the right place. So in that case, there's no error function yet, but we pretend we have an error function, return error, closing bracket expected. Right, so that's a return, and that will just basically blow up the program. What am I doing? No, that's right. Oh, I'm confusing myself because of the brackets and the brackets. Closing bracket expected. Right? So that's what happens there. Otherwise, we do ts.get again. And we return E. Oops, not in here. So we do ts.get again, and we return the value of E. Hopefully returning the value of E makes sense because we're trying to like when we get to this is the primary we're trying to evaluate. So this e value that we got from here is what we're trying to return. And the reason why we do ts get again is basically to eat the right parentheses. Get rid of it from our, right? Because right now our current is here, like we talked about, but we don't really want it to be there anymore. We'd rather sort of go across to the next token, so we just call ts get to kind of get rid of it. And that's also the reason why, for example, the number case had the ts get in it, even though maybe it wasn't strictly necessary, because in essence, because one of the cases has an extra ts get in it, you want all of the cases to have an extra ts get in it, because you want that kind of consistency, a kind of predictability, so that you know that no matter what case you're in, you're always going to read the next, like an extra character, basically, an extra token, I should say. Same, and so if you look at the name, code, it also has a ts.get in it as part of its conditional. So it's also going to read an extra character, regardless of whether the equality of kind assign is actually true. Does that make sense? Like, it has this line: ts get kind equals kind assign. It's always going to run that every time, regardless of if this condition is true or not. So that in all the cases, it will in all the cases it runs ts.get. Even in the minus, it's not explicit, but remember that you called prim again. So you expect that in that prim call, it will probably run a different case and run that extra ts.get. There is also a default case. I also need brackets, actually. I need parentheses. I need the squiggly brackets, sorry, here and here, because again, I'm doing my initialization. There's also a default case. I won't bother writing it properly, but essentially, default means you've hit an error, because you've exhausted all of your definitions, right, for primary. So if you hit a default case, that means none of the definitions matched, which means you've made a mistake. The user's made a mistake with their input. Okay. Now, that's the prim function, and hopefully it's clear, or at least you're convinced that it's able to evaluate whatever primary we want, including the weird expression recursive one in brackets, even though we haven't explicitly looked at the expression function yet. Okay, next we do the term function. So if primaries are able to evaluate those tiny primaries, terms are now evaluating the combination of primaries to make terms. So we have it returns a double again, term, and again it takes in this get parameter. So we begin by having double left equals prim get. Okay, so what's happening there? Remember that if we hit a term, that means it looks something like this. It's going to look like a primary, either times or divide another primary, times or divide another primary, and so on, right? Let's leave it there. So, what do we expect? We expect that the primary will be evaluated in prim, and remember that the extra ts.get will always be run. So we expect that our current token will be here. Because the prim function would have read that an extra ts.get after the primary, and so would have gotten to the either the times or the division, right? So, what are our cases? Remember that we either have a multiplication or a division here. So, case... Oh wait, I forgot to switch. Switch ts dot current. This is my point. We do current, not next, not get. Sorry. Dot kind. So if the kind of our current token, this one, is a multiplication, so it's an asterisk, then we can do left times equals prim, true. So what's happening here? And we break. We break. I forgot the while. Okay, there's a while true loop as well. Sorry. So sorry. After the double left, there should be a while true loop, and then we get into our switch case, and that's why we break. Okay, so let me break it down again. So what's happening here? We've seen that there's a multiplication here. That's what this case multiplication does. So then we evaluate the next primary, right, using prim, and we multiply that primary to left, which would have been originally just been this primary here, right? And remember that prim always calls the extra get. So by the end of this prim, we would actually be there, right? And we call left. So we multiply that prim to left. Times equals means make left equal to left times prim. Make left equal to that, and then we break out of the switch. But we stay within the while loop. Remember, break only breaks out of the innermost scope. So we break out of the switch, but we stay within the while loop so that we can continue our loop, right? In a similar case, let's say we're back here. Instead of multiplication, what if it was division? So instead of a what if we saw a forward slash div? Yeah, okay. Then, same kind of deal. Left divide equals by prim true. Okay? And we break. And notice that we're setting prim to true all the time here. Like, as in we're setting this argument to be true, not get, so like we're using true. Because we know that the current is here. So prim's going to definitely have to read the next character, next token each time when it gets called here in this situation. So we set this to be true. And same kind of thing. So, we say, left is here, left is this value here. We've seen the division. So now get this next primary, evaluate it, divide left by this primary, and then break out to start the loop again. And remember that the current would now be set to here, because prim will always call the extra TS they'll get. Finally, we have default, which means we haven't hit a multiplication or a division. Which means, in this case, it's not an error. It just means that you've run out of primaries times primaries times primaries. Maybe there's a negative in there. In which case, let's say it was a negative, and then you had some other expression, right? Some other expression on that side. All that means is the term you made was here, right? This is the term you had to evaluate. That's what this function is supposed to evaluate. And then from there, this overall thing is an expression, right? Term minus an expression, where a term is a special type of expression, so it's actually just an expression minus an expression. Wait, no, I said that wrong, sorry. This term is what you had to evaluate, and then you're just going to do term minus expression, which, was that what the definition looked like? Expression minus term. But remember that term is also within the expression definition as well. So this overall thing is just an expression and will be evaluated by the expression function. Don't worry about that too much. That was actually really stupid of me to say. But just for now, just understand that if we hit something else, like a minus sign, for example, and we get to our default, we haven't actually, it's not an error, we've just completed the term evaluation. And so we just have to return left. This one, and then we see this, and then this. So notice that we have a while true loop because essentially we don't know how many times we're going to have to do primary times or divide primary like that. We don't know how many times, so we just loop along around over and over again until we no longer hit a multiplication sign or a division sign. Okay. And last function is the expression function. So this is basically the same kind of structure as the term function. In the sense that, so it returns a double, we call it expression, expr, bool, get. So double left equals term get, right? Because we expect an expression similar to the relationship between terms and primaries. We expect an expression to look like a term, plus or minus a term, plus or minus a term, and so on, right? For as long as we need. So in a similar structure, while true, because we don't know how many times we want to do it, switch on ts.current.kind. And again, we use current here because we expect term to be completely evaluated, and then the plus or minus to be what kind of gets read in next to determine. We expect the plus or minus to be read in because that's how we know that term ended, right? The term can only figure out it ended when it reads in something that isn't part of the term. So it has to read the next character in, which is the plus or minus. So we look at what the consequence of that is. We do current here, not get. We check the current kind, and in a similar sense, if the case is kind plus, if the case is kind minus, and then default, we have left plus equals term true, and then we break. Otherwise, we have left minus equals term true, and then we break. And then we have return left default. So very, very similar to the term function, right? It's just using pluses and minuses. And again, hopefully you can see why the BODMAS rules get followed, especially for the for operators, like why division and multiplication happen first. Because, in essence, whenever we see term plus or minus, whenever we evaluated the term, right? We said this, plus or minus, if we see another term, we evaluate that term first. And that term will consist of divisions and multiplications. So all that stuff, all the divisions and multiplications will be evaluated within this term first before it gets added or subtracted from this term over here. That's why BODMAS kind of gets followed. And that's something to bear in mind because the order of operations, both in this calculator but also for programming languages, is important, right? Being able to have a definitive order of operations. So having your definition structure like expression, then term, then primary or whatever, it's important to have that because then you can kind of really clearly describe your order of operations. Yes. So that's basically the same thing as what we talked about with the term function. It's pretty much analogous to the expression function. So it can kind of be thought of in the same way. Yeah. Okay. So that's all of the functions to do with evaluating. Sorry. It's all the functions to do with evaluating. So expression, term, and primary. Those are able to handle evaluating entire expressions and entire primaries and entire terms. Okay, so what is the missing pieces? Given a bunch of tokens, we're able to now evaluate our expression, right? Which is great. Our only issue is that the tokens, we have to know their kind, right? We have to know their number value and string value if they have them. And we kind of just pretended we knew them, right? We just said the get function was magical. We didn't really think too much about it. So the question is, how do we now handle getting tokens and checking the current token? Like, how do we actually do that? So that's what 10.2.2 is about, and this is kind of that input function part, where we figure out how to kind of interpret our input without necessarily doing any evaluation yet. So this is 10.2.2, which is the input. So this is where we define the token stream class, right? We said that the token stream had a get function and a current function. Sorry. A get function and a current function. But this is where we actually define those things. All right. So we have class token stream. In public, there's one extra thing we have to write in the public section, or two extra things. There's token stream I stream %s. Okay, this is some weird syntax that we haven't looked at yet, but I will do my best to explain. Okay, so what's happening there? Remember that in terms of our input stream of characters that we're giving to the program, has to come from somewhere. Normally we expect it to be from standard input. This is a really cool way that you can actually set where the characters are coming from. So an I stream, I just spat everywhere. An I stream is input stream, can be described, is actually something that you can point to or you can refer to using a variable in C++. So that's what this is. An I stream, for example, stdcin, right, standard input stream, that's a type of I stream. That's a type I stream. So you can pass the standard input stream, or like a reference to it, as an argument, or give it as a parameter, and we will save that in a variable called IP, a member variable called IP, which we'll define below. And owns, in this case, because we're using a reference, owns is false. That's to contrast it with if we gave a pointer, I stream pointer p, then we set IP to be equal to p, and we set owns to be true, right? Oh, and we need to give an empty body. So IP being equal to p, basically we're saying, given the pointer to the stream, the standard input stream, for example, make IP, this below property that I haven't given yet, make it equal to that pointer. And now we do actually own the resource, essentially, because chances are in order to get this pointer, we use some kind of memory allocation on the heap. And so we will probably have to be the ones to make sure that that memory is deallocated. We'll talk more about memory allocations later, but yeah. And this syntax, I don't think we've seen before, especially with constructors where you have like certain variables that you want to set or initialize to input arguments, input parameters. You can have, instead of like putting it in the body, that's what this is. This last thing is the body. You can have colon after your sort of your constructor like definition or whatever, your constructor signature, I guess. You can put a colon and then put like the property that we haven't defined yet, and then the value that is being passed in from the parameters to this. And you can comma separate that. So IP is the input pointer or something. I don't remember what IP stands for, but anyway, IP, which is our property, is going to be set to the address of S, which was actually a reference, but the address of S, and then owns is going to be set to false. That's what this is saying, and the same thing below here. So we're actually keeping the body empty, and we're also going to use we also have a destructor. So that's what is it? Tilde, I think. Tilde, and then token stream, and then we're just going to call something called close, which we will define as well. Okay, so what I will say is, these three are like class-related things and important to make things work. But for now, if you just write that stuff, it will work, and I wouldn't expect as much understanding as later, as if we read the book a bit later, a bit more of the book. Then we have token get, so the get function, and we have token ampersand current, the current function. So we've seen this before. Get, I'm still not going to implement just yet because it requires way more of the board. But current, we will say return current token. Okay. What is current token? Again, I have to define it below. So these are all the public things. So constructor, and then the get and the current. These are all public things. Private includes the close function I mentioned up here. So void close. This is my body. If owns, then delete IP. Okay. So again, this delete keyword we haven't really talked about yet. The glare is getting annoying. If owns, delete P. But essentially, if we own the resource associated with the pointer stored in IP, if we own that resource stored in IP, then we have to explicitly ask for that resource and the memory to be deleted. Well, we don't delete the memory, but we no longer associate ourselves with it, essentially. So that's what the delete IP does. Now, we have iStream pointer IP. So this is where I've introduced the IP. So that's what this IP is here, and here, and here. It's a pointer to an input stream. Okay? Bool owns. So that's the owns is here and here. Essentially, we're asking, do we own the actual memory that IP will be pointing to? And if a reference is passed in, then we won't be the owner because someone else should be owning it if we're giving a reference. But if we're given the actual pointer, then that means we will be the owner, right? We have the pointer. We have the actual pointer to the address. So that means we own it. And so we should only delete IP if we got the actual pointer, not a reference. Because if we got just a reference, that means someone else probably has the pointer. And finally, token, current token. And we actually do an initialization here as well. Kind end. So this current token is what, not current, sorry, just cur. So this cur token is what this one refers to. So when we say current, we're actually returning this guy over here, a reference to this guy over here. And we're initially setting it to be the end token, right? Token of type end. And so what this means is, like, every time we read in a token, we can set this current token to be equal to that new token, and then we can get that, and we can retrieve that current token using the current function. That's what this is. That's what's happening here. Okay? And then we have to close off the class definition. Okay. So just to reiterate, constructor lets you set where the input stream is and whether we own it. This is more like slightly lower level, making sure the memory is allocated and deallocated correctly. The destructor relies on this close function, which basically makes sure that the memory is correctly deallocated if necessary. IP stream is just so that we can make sure that we are able to access the input stream, right, where the user is plotting in characters. Get, we've talked about, it's the magical function that can retrieve the next token, however long it is. And we will talk about its implementation in a second. Bool owns is part of the memory allocation thing. Token, current token, stores what the most recent get token retrieved, right? So that's what token will store, and current will return that current token field because that was the most recent thing that get got. So in that sense, that's what token string will do. Now, I believe, now we get to the really scary one. Now we get to the really scary one, which is defining the get function. So a cool thing you can do, this is a bit off to the side. You don't necessarily have to actually write definitions of functions inside this class, because what you can do is outside the class scope, you can access the class scope by doing the resolution operator. So token stream get. That means we're accessing this get, and we're going to define it here. And then it also returns token. So we put the return type here. Then we access the get function that we declared it but didn't define it, and we use the resolution operator. Okay, this is quite long, so I want to make sure I give myself enough space. Okay. Let's see if I can do this. We start by introducing and initializing a character variable, right? I'm setting it to the null character for now. And the idea is the character variable is going to figure out what the next character is, right, in our input stream. Remember that not all tokens are one character, so it's not like once we read in a character we've got the token, but it's a good first step, getting the first character. Okay. There is a do while loop, which I know we said we should avoid, but can you do? If not IP get ch. Okay, so let's be a little bit careful here, because I feel like we've used the word get a lot. This get is actually a function associated with the iStream type, not the token stream class, right? So remember IP was the pointer that pointed to an iStream, right, an input stream. So we're basically accessing, right? Remember, this is like the dereference and access operator. We're accessing the get function associated with the iStream class, and we're passing in ch because we want to get ch to be set to the character that is read in from the input stream. So if this is the case, so if it's not the case that we are able to do this properly, then we simply set current token to be equal to kind end, and then we return current token. Okay, hopefully that makes sense. In essence, we're reading in the next character in the input stream by doing this, but if it's not a valid character, right, because it's like something weird, like a control D kind of thing, or what else? I would assume nonce on it. I don't know how you would even do that, but yeah, if it's like a weird character, then we'll run this and we'll just return current token. But current token has been set to the end type, right? So current token refers to the current token in the token stream class, but we're going to set it to be the end token, and then we want to return that. Alternatively, we can actually write this in a slightly different way, in a slightly abbreviated way. Instead of writing it in 2 lines, we can just say return current token equals kind ... end. These 2 things are equivalent. These 2 lines up top versus this bottom line down here. Essentially, the assignment happens first, and then you return current token, which has been set to kind end. It's kind of like having a declaration in your if statement. It's like the initialization, whatever is on first, and then whatever that value was is used for the Boolean evaluation. So yeah, you can write like this as well. And in fact, since we can write it in 1 line, I will do it like that. So you can return current token equals kind, equals bracket kind dot, right? Because current tokens are struct, so we can do it like that. And then close the while the character is not equal to new line and is space. I think it's by the standard library. So it might be std is space ch. Like this. So this whole point of this code here is basically to be able to read in like white space characters, and yeah, that's pretty much it. Like, because for example, let's say a user says space r equals blah blah, right? So there's a bunch of space. We should be able to read this in no problem, but the spaces make it annoying, right? Because like, how many times I have to read in space before I actually hit my name in this case? So that's what all this is. While ch is not a new line, and we're actually reading in spaces, let's just make sure that we don't read in anything weird. And then when we finally don't hit a space, we'll break out of the do while. That's all this is. Okay, so this is like an extra check just to make sure we're able to read in space characters and kind of just throw them away and ignore them before we get to the actual tokens. Okay, now we switch. Yeah, I'm not gonna have enough space. Okay, I'm gonna erase that do while. It happens. I'm just gonna give space. And note that the IP member function the IP get ch thing reads in the characters for us as well. So ch will be set to the character that we want to read in, which means we can do a switch statement. Switch on the value of ch. Obviously, it was set to 0, but again, IP get will change its value to the most recently read in character. So we read in this. If it's still case 0, if it somehow is the null terminator, then we can simply, just like we did in the while loop, we can simply return ct equals, not ct, sorry, token equals kind end. Right? No nonsense, because if it's a null terminator, which is what 0 means, if it's a null terminator, then you should just end it. Now, if you have case semicolon or case new line, then you can return. Then you can return current token equals kind print. Now, this is kind of interesting. Back when we talked about switch case statements, we talked about how, like, generally you want to avoid the cascading effect, right? Because normally that's not expected. And so we put breaks everywhere, right? Breaks in all our cases. In this case, the return kind of acts like a break here because, like, we're returning, so essentially we're breaking out of the switch case, and then returning back to the function caller. But yeah, normally we have some kind of break out of the switch case at the end of every case, right? But here, since semicolon and new line, whether someone types in an expression, then hits semicolon and hits new line, or if someone just hits new line straight away, it should do the same thing, right? We would expect that the printing gets done, because semicolon kind of traditionally is supposed to represent the end of the expression, but maybe someone forgets and they just hit new line straight away. Either way, we would want printing to happen, right? And so, because they have the same functionality, we can actually rely on the cascading effect. Either it's case semicolon, in which case we cascade down to this guy and then return, or it's new line, in which case we just run this anyway, but they both have the same functionality. So in that sense, the cascading effect is actually useful. In a similar fashion, we can do something like this. Case multiplications, asterisk, colon. Case division, colon. Case plus, colon. Case minus, colon. Case open bracket, colon. Case close bracket, colon. And finally, case equal, colon. I have just taken all of the tokens or characters that have, these are all the characters that have corresponding kinds in the enum class. What do I mean by that? These are the characters that were assigned to very specific enumerators, right? So mul, for example, was set to the multiplication. Div was set to the division. I assume plus was plus. Minus was minus. LP, RP, and assign were all given these exact characters. So we can use the cascading effect here and do the following. Return current token equals static cast to the kind type, the enum kind, the kind type, ch. Okay. So whereas before we might say, current token equals kind end or kind print, we're saying current token is equal to this kind of ch, and we're doing a static cast. So for example, if the character was a plus, right, we would do a static cast from the plus character into the kind type, giving us the plus enumerator, and then make current token equal to that kind, and then returning the current token, right? So it's a kind of a clever way of using a static cast in order to handle all the cases at once. So multiplication, division, plus and minus, LP, RP, and assign, right? All of those will hit this case due to the cascading, will hit this case, and get cast to the corresponding enumerator in the enum class, and then will be assigned to current token, and then that current token will be returned, right? And hopefully it's clear that that's all they all want that to happen, which is fantastic. And notice that we have to use static cast here because there's no implicit conversions, because kind was an enum class, right? Not a plain enum. So that's the other thing. Okay. Now, in a similar sense, we're going to handle all the numbers. So I'm just going to get rid of all of this. So those are all the cases for, 0, print, and all the sort of operators, all the like multiplication, division, etc. Now, the other thing you have to handle is numbers, right? So case 0, case, it should be in single quotes because it's a character. Case 1, case 2, case 3. There should be colons at the end of each case label as well. Case 3, case 4, case 5, case 6, case 7, case. Well, I'm putting colons in all the wrong places. What am I doing? Case 8, case 9, and don't forget case decimal point, because all of these are part of our number, right? Okay, this bit's kind of weird, I'll be honest. But this is one of those times where kind of have to just allow it. Essentially, we rely on the powers of the iStream class to handle this for us, of the iStream type. So, in essence, we say IP, we access the put back function, and we say ch. So, without knowing exactly how put back works, essentially it puts back the character at the front of the stream, right? It's reading in the stream one at a time. Oh, we hit a number, let me put that character back at the front. That's what that is. And then we dereference the stream and we redirect it to current token dot number value. So let's say the input stream looks like this, and then plus 9 minus r or whatever. Let's say that's my input stream. it will see the 1, hit this case, cascade down to here, put the 1 back, and then redirect as much of it as it can into number value, right? As much of the input stream as it can into number value. Now, I don't know if C++ is really clever or computers are clever in general or what, but for some reason, it's basically really good because number values of type double. This line is really good at making sure the biggest double available will be redirected and cast into a double and then set to number value. Sorry. So number value will be set to the biggest double that can be made in the input stream at the moment, right? So as soon as it sees that plus, it goes, oh, that's not a number or whatever. Maybe it's in a similar way to what we do here. It goes case by case and makes sure that while it's either like a 1, or a number, or a decimal point, it will make that value part of the number value. But then when it sees a plus, it goes, oh, not anymore. So this really accurately gets the double value we want, casts it into an actual double, and then sets number value to be equal to that double, right? Which is what we want. So basically, all of this will be kicked out of the stream, and we'll be left with the plus 9 minus r thing. Okay, so that's what that line does. We set current token to be equal to kind number, and then we return the current token. Notice how this time we didn't actually use the same syntax as before. Before we were saying return current token equals kind blah blah. We don't do that this time because we've set the number value to be something. So if we instead did something like this, right? If we did that, that's a problem because current token originally should look like this, right? It should have kind number, and the number value should be set to something. 1, 2, 3.45, whatever, right? That's what we want. But when we run this, what happens is this is the new struct, basically. This is the new struct. Remember, current token is a struct type. So basically, we override the entire assignment with just this. We basically lose the number because we've reassigned token just to have the the number kind, but not any number. So all this work up here is lost, which is why we do the kind assignment as a separate thing. So current token dot kind equals kind number. Okay, so that's that one. So that's how we handle numbers. And then finally, we just use the default case. Because essentially, if it's not a number, and it's not one of the symbols we wanted, then it's either an error, or it's a name, right? Like area, radius, or whatever. So we kind of handle that in the default case. I keep forgetting to use this guy. Default. Default. Now, if is alpha, this is another standard library function that's available. If we look at the character and it is an alphabetic, it is a letter of the alphabet, right? If it's one of those, then we're pretty confident that it's going to be the start of a name, like area or radius, right? If this is the case, then, another penguin. Might be worse. Then, current cur token dot string value will set it to be equal to ch, right? Because ch should be the start of the name. So for example, if it's radius, this is our input stream, right? R-A-D-I-U-S. Basically, ch would have been set to r, and we will set the string value, so current token, which will originally be set to just r by itself. That's what that's doing. Cur token dot string value equals the ch, equals that first letter. Now, while ip get ch and, just write it underneath, should be the same line, while it still is alpha num. So this time we're allowing both letters and numbers, because, like, for example, you might have radius 1 as one name and then radius 2 as another name. So that's fine. We just don't want names to start with a number, kind of like with normal C++, right? We want it to start with a letter or an underscore. In this case, we don't care about underscores, I think. But yeah. So now while we are able to get a valid character and it is alphanumeric, then we can do CT, current token plus equals current token dot string value plus equals ch. Right? So what this while loop is doing simply is iterating through our radius letter. So, like, we're going to the next letter. Oh, it's still alphanumeric. Yeah, sure. And we go to the next one. Oh, it's alphanumeric. Sure. Alphanumeric, alphanumeric, alphanumeric. And then maybe there's like a plus or something. In which case, it's still a valid character, but it's not alphanumeric, so we stop there, right? And therefore, current token's string value is equal to radius, which is what we wanted. So this is just a way to make sure that we get the entire name. Then the only reason we would break out of this while loop is because, for example, we read some extra character, like a plus, which we would check this, so we get it, and then we check if it's alphanumeric. It's not, so this guy doesn't run, but we have actually gotten the plus. So what we do is we say IP put back the ch, because we're going to put back the plus in the input string because we don't want to deal with it. Then ct dot kind equals kind dot name, and then return. Oh, not I keep saying ct. It's in my notes as ct. Current token, and then we return current token. Right, so we successfully managed to set the string value to be the correct name, and then we set the type to be name, the kind, to be name, and then we return the current token. Now, that's if this guy is alphanumeric. But if it's not alphanumeric, then that means there's some mistake somewhere. So we return an error. Oh, no, we don't return an error. We just call the function error. Bad token or something. And in the example, there's also they return the current token of type of kind print. So you just kind of try print whatever you want and move on to the next expression in the expression list. But for now, I'll just let it write like that because I'm out of space. But the more important part is this part, being able to evaluate or be able to figure out what the name should be based on the input stream. So that's what that is. Obviously, the switch case should also be closed off, and the else should be closed, but that's the general idea. So that's pretty much the entire get function. This idea of being able to use a switch case to figure out, is it a number, is it a name, is it a symbol, is it like an end of line, like a new line or a semicolon, is it one of those? And then from there, handling on a case-by-case basis what the type, what should the current token be set to, and then return that current token so that the user can see it. So that's what that is. And we're almost done. There's a quick thing on error handling. Basically, I've mentioned this error function a couple of times. The way that's done in the program, 10.2.4, is essentially we have a global variable, int number of errors, and then we have double error is it double? So returns a reference to a string. That should say const string reference to called s, and then every time this function is called, we increment the number of errors, and we say we write the standard error stream. We write error, and we redirect this s string, and then we put a new line in there. What am I doing? Error space redirect the s, and then redirect the new line, and then we just return 1. I'm really not sure why this is double. Maybe it's conspicuous. Okay? Well, in essence, in this case, the number of errors is the global variable, and essentially every time the error function gets called, we increase the count by 1, and we just print out the error that we provided, like the error message that we provided in here. We print that to standard error, the standard error stream. So that's, yeah, simple enough. And finally, with the driver. Driver is kind of more of a formality. I feel like we've gotten the really hard nitty-gritty details we've kind of got through. The driver is kind of like it's a requirement, but it's not as interesting, so to speak. Driver. So essentially, the entry point, right? So for a C++ program, it's like the main function. So we'll start with int main. Int main. So, you know what I should do first? I'll just talk about. I'll just say. I forget exactly what the syntax is, but it'll be like map string double table. And I assume you have to I think that's the default constructor anyway. Alright, so that's the table global variable that we talked about before. Now we'll say int main. And then you have something like table, and we'll say pi equals 3.1415. Right, so this is how we preload the name pi into the calculator before the user has a chance to do anything. Same with, he also uses Euler's number. So E equals 2.7, 1828, right? So we preloaded pi and E into our map, into our table, and then we call a calculate function, which we'll write up in a sec, and then we return the number of errors. Remember that when we were talking about the errors thing, that was the number of errors is a global variable, so main will be able to access it, no problem, right? So that way, the return value of main is the number of errors that were created. And the calculate function, first things first, right before the calculator function, we have token stream ts, right? Remember in the get, in the prim function, and in the prim, the expression, and the term function, we kept talking about ts current, ts.get, whatever. So we define ts as a global variable, and in this case, we set it to be equal to cin, right? So we are setting the token stream to be looking at the standard input stream. And then we have the calculate function. So this will be defined before the main function. Void calculate. So while true, because we don't know how many expressions they're going to be in our expression list, while true, we call ts.get, because we have to check some things, if ts.current.kind is equal to kind end, right? If we've immediately just broken the program, remember the expression list can be empty, so maybe they just hit Control C straight away or something. Then we can just break, right? Break out of this while loop, and therefore just basically return from the break out of this while loop. Otherwise, if ts.current.kind is equal to print, right? Maybe they just hit enter straight away or semicolon straight away. Then we continue, right? We move on to the next iteration of the loop, the next expression in the expression list. And if neither of these two things are true, then we're pretty confident that we've got an expression to evaluate. EXPR, so we evaluate this expression using the EXPR function, and we actually set the get parameter, the get argument, to be false, right? Because if the expression looks something like this, right, with a bunch of terms, plus minus a term, plus minus a term, etc. Because we already called tsGet, we've already looked at the first character or the first token of our term. So there's no need to like re-get that first token. So that's why here we set this guy to be false. Because if prim calls, because prim is what uses the actual parameter. If this is set to true and prim calls ts.get again, then it's actually going to move on from the first token to the second one in the term, and that might cause problems, and that will cause problems. So this is actually set to false at the start, and that's why we need that get, because most of the time it's set to true, but at the very, very start it needs to be set to false. That's why we have that differentiation. Okay, so that's pretty much the entire thing. The only extra bit of detail I forgot to say before is remember that expression calls term, and term calls prim, right? Like there are prim calls in term, and there are term calls in expression. Remember that prim calls expression in one of the cases, the parentheses case. It calls expression. What is the consequence of that? Well, if you were to define prim first, so if you were to do prim brackets, blah, blah, and then do term brackets, blah, blah, and expression brackets, blah, blah, the definition of prim is complete, so term can use prim no problem, and the definition of term is complete, so expression can use term no problem. But then the expression, the expression function hasn't been introduced yet when we're reading prim. So the compiler's going to have a problem because it's going to be like, what the heck is expression? What is that EXPR function that you're talking about, right? So to get around that, what we have to do is we have to declare the function expression like this. Be like double boolean get. So we declare it without giving any body. We just declare it. And now that the name has been introduced, similar to the structs idea, now that name has been introduced, prim can use the name, and the compiler will be like, okay, I don't know the exact definition yet, but I know that the name is there, so I will allow it for now, right? And then when it sees the definition down there, it goes, oh, that's the definition you want. Okay, we can use that. So you have to declare without defining, you have to declare the expression function so that prim can use it, and then once prim is done, term can use prim, and then expression can use term. So that's it's kind of like a cyclical dependency. So you just have to make sure that above declaration is there. Okay, I reckon, how long did that take? Less than 2 hours. How long was the other one? You know what, maybe one video is enough. Because I feel like this will take max 3 hours. And so it's like a 5-hour video, which is like a bit long, but not as long as I thought. I thought it would be like closer to 6 or 7 hours. Okay, cool. I'm going to stop this though, because I'm tired.